So this problem reads that we have a closed, rigid tank containing 3.5 kilograms of air initially at a temperature of 300 Kelvin and a pressure of 1 bar. The air is heated by a thermal reservoir, and the heat transfer occurs at a boundary where the temperature, so the boundary temperature is 600 Kelvin. A stirring rod stirs, and they give us the amount of work is 225, and that negative sign indicates that it's not from the system, but it's into the system, and the system being the air. Okay, the final air temperature is 600 Kelvin. The air can be modeled as an ideal gas with the C sub V equal to a given value, 0.733 kilojoules per kilogram Kelvin. Kinetic and potential energy effects are negligible. Determine the amount of entropy transferred into the air. Well, how is it being transferred into the air? It can only be transferred with the heat transfer. And so what we're asked to solve for is, and you can make up notation for this, but the entropy transfer with the heat transfer. It's like S with the Q. How would you calculate that? Well, you would find out, because the boundary temperature is constant at 600 Kelvin, we don't have to do a complicated integral with the changing boundary temperature, but it just boils down to what is the amount of heat transferred divided by that constant boundary temperature. Okay, so for part A, we want to calculate the amount of heat transferred into the system, into the air, as it undergoes a process. So we could make a sketch like this. This would be a rigid tank. The focus of the study is the air in it. We have a stirring rod or paddle wheel that stirs it up, transfers energy by work into it. And then we also have a thermal reservoir. We could put it right here in contact, and there's a heat transfer. So if you want this boundary temperature here, TB, is 600 Kelvin, and we have a Q going in during the process, as well as, I'm going to show it like this, a positive work going out, but that positive work going out is negative 225 kilojoules. Okay, so we do an energy balance, or first law. For the air is a system undergoing a process, we have that the mass of the air times the final internal energy, initial internal energy, so it's a change in the internal energy, equal to heat brought in minus the work transfer out. Okay, and you can put 1, 2 on this. I'm just emphasizing it's during the process from initial state 1 to final state 2. Okay, so if we're interested in calculating Q1 to 2, that's equal to the work 1 to 2 plus the mass. And because they give us a specific heat right here, we're going to go ahead and use that specific heat. And so we're going to calculate the change in U as C sub V, the change in T. All right, so let's substitute some numbers. Negative 225 kilojoules plus our mass, 3.5 kilogram, specific heat constant volume for the air, 0.733 kilojoules per kilogram Kelvin. And then the temperature change. The final temperature is 600 Kelvin. The initial temperature is 300 Kelvin. Then we just cancel our kelvins and our kilogram, and we calculate Q 1 to 2 is equal to 544.65 kilojoules of heat transfer in. All right, now we come up here, we say, well, what is the entropy transfer with that heat transfer? Well, it's equal to Q1 to 2 divided by TB. So 544.65 kilojoules divided by our boundary temperature, 600 Kelvin. And that gives us the final answer of, and I'm just using this notation. You can use a different notation for the answer. 0.908 kilojoules per Kelvin. Answer for part A. All right, continuing, what is the amount of entropy produced? Well, the book uses sigma, and I like to add the subscript 1 to 2 for the amount of entropy produced during a process from initial state 1 to final state 2. Another textbook, popular textbook for this type of class would use SGen. All right, so what do? Well, we used the first law already for the process and energy balance. Let's use the second law for the process. That's an entropy balance. Instead of energy balance, entropy balance. And so we'll have that the mass S2 minus S1, so that's the change in the entropy in the system. We can have entropy transfer in, I'm going to write it like this, Q divided by TB, and we already calculated that. That's this answer for part A. That would be bringing in entropy with the heat transfer, and there's no entropy transfer with the work, and the only other entropy term in here is that we can have a generation, an entropy production term in the process 1 to 2. Okay, so we're interested in solving for sigma 1 to 2. It's equal to the mass S2 minus S1 minus Q over TB, which you already know the answer to. Actually, another good symbol, instead of using this symbol for the answer right here, we could just have used Q over TB and let that be what we're solving for right there. Okay, well, how do we solve for the change in entropy? Well, there's a lot of different equations to be used to solve for the change in entropy of an ideal gas. Let me show two equations which are very popular. So S2 minus S1 is equal to C sub P natural log of T2 over T1 minus R natural log of P2 over P1. Then another one, S2 minus S1 is equal to C sub V natural log of T2 over T1 plus R natural log of V2 over V1. And if you don't, in another equation, if you don't like constant specific heats, you can do S2 minus S1 is equal to S2 naught minus S1 naught minus R natural log of P2 over P1. Okay, you want to be familiar with all three of these equations. And if you're using constant specific heats, that's the most popular equation. And if you're using variable specific heats, meaning you need to use a table to look up these S naughts. And the table would, in our textbook, is table A22. And again, why would you use that table? Because it's accounting for variable specific heats, temperature dependent specific heats. It's a little more accurate, but there's great value in using a simple analytic expression like either the first equation or the second equation. Okay, both of these equations are popular. Like this first analytic expression here is a little more popular, but you need to know the temperatures and the pressures, initial and final state temperature and pressure. And we don't know the final pressure here, but what do we know is that it's a rigid tank. And after you solve a few of these problems, you realize, oh, if it's a rigid tank, did the volume of the tank change? No. And the mass didn't change. It's a constant, it's a closed system, so the specific volume didn't change. And in cases like that, the second form of the equation is more popular because this is the natural log of 1. That whole term is 0. So if you want to solve for it, this is the best way, or for this problem, also you're given C sub V. When you're given C sub V and not C sub P, think about using this second equation right here. Okay, so let me just write it like this. I'm going to come up here, and we have the sigma 1 to 2 is equal to our mass times C sub V times the natural log of T2 divided by T1. Then we have our minus Q divided by TB, substitute numbers. So what is our mass? 3.5 kilogram. I'm going to have to drop units. I don't have a lot of space. And our specific heat constant volume, natural log, our final temperature, 600 Kelvin. Initial temperature, 300 Kelvin. And we subtract the 0.908 kilojoules per Kelvin, and the entropy generation during this process turns out to be 0.871 kilojoules per Kelvin, the answer for part B. So this is the form of the equation that we use. I know it can be confusing, like how do I calculate the entropy change for an ideal gas like air? Well, you can use a table again, or you can use either of these two popular equations. The first one is a little more popular, but you need to know temperatures and pressures. If you have a rigid tank, the volume doesn't change, specific volume doesn't change. That's when this form is more popular. Well, hopefully that's helpful. Thank you.